In this problem, we want to design a spam filter, and one way to do so is to come up with phrases that are more likely to occur in spam versus non-spam email. And so when we get an email, we look through it, and if we find some of these phrases, we think that the email is spam. And so one such phrase might be, for example, free money. So if we see free money in an email, we're likely to be suspicious and to think that this is a spam email. So suppose we have a list of 100. So we have a list of 100 of such words or phrases. So for example, free money, or we could have, like free stuff, basically. And we have 100 of these phrases that we use to identify spam email. And we're going to define an event. We're going to say let wj be the event that an email contains the jth word from this list. So this is the event that jth word or phrase, so whatever we have there, is in the email. And we're also going to say the prior probability that the email is spam is little p, and we're going to define little p sub j to be the probability of this jth word from our list being present, given that the email is spam. And we're going to define r sub j to be the probability of the jth word being present in the email, given that the email is not spam. Now, we're also going to assume that all of these words, this 100 words and phrases in our list, are conditionally independent, given that the email is spam. In other words, knowing that the email is spam, knowing that the jth word occurred, tells us nothing about whether this ith word has occurred or not. So this is equal to the probability of the ith word occurring, given that it's spam. So where I is not equal to j. So if we take two different words or phrases from this list, given that the email is spam, they are conditionally independent of each other. Knowing one has occurred tells us nothing about whether the other has occurred. So this is a very strong condition, because in general, if you look at an email and you know it's spam and you start reading it and it talks about, let's say, Bitcoin, then you might assume that other phrases from your list regarding receiving free Bitcoin might be in that email, that they become more likely. So under this assumption, we're saying conditionally all of these phrases remain independent. And this is a naive assumption that is a good starting point, but because it's naive, this technique is known as naive Bayes classifier, where we try to classify whether an email is spam or not. So using this technique of naive Bayes classification, our goal is the following. So we are told, we receive an email, and we're told that the email contains the 23rd word, 64th word, and the 65th word from the list. Are in our email. And we'd like to know the probability that the email is spam given this information. So we'd like to know the probability that the email is spam given that W23 has occurred, W64 has occurred, W65 has occurred. But then for the remaining W's, the complements have occurred. So the remaining words are not on the list. So we have W1 complement, W2 complement, etc. up to W100 complement. So to compute this probability, we're going to use Bayes' rule. We're going to say this is equal to the prior probability of email being spam times the probability of seeing this word distribution, so seeing the 23rd word, the 64th word, 65th word, and not seeing the remaining words from the list, given that the email is spam, over now by the law of total probability, we can copy this over. So probability of spam times the probability of seeing the 23rd, 64th, and 65th words and not seeing the rest, given that it's spam, plus the probability that the email is not spam, so probability of spam complement, times the probability of seeing 23rd, 64th, 65th words and not seeing the rest, given that the email is not spam. So the probability of seeing 23rd, 64th, and 65th words and not seeing the rest, given that the email is not spam. Now we can start plugging things in. So the prior probability of an email being spam was p, little p. And now we can use the conditional independence. We were told that conditioned on the email being spam or not spam, the occurrence of the words from our list in the email are independent. And so what this means is that the probability of the 23rd word occurring, 64th occurring, 65th occurring, and the rest not occurring is just the product of the individual probabilities. So this is the times the probability that the 23rd word occurs given spam, times the probability that the 64th word occurs given that our email is spam, times the probability that the 65th word occurs given spam. And I'll just write ... meaning we're going to multiply the probability that the first word doesn't occur given spam times the probability that the second word doesn't occur given spam, and so on. And we're going to rewrite this expression in the denominator. So probability of spam again, p times probability 23rd word given spam times probability that the 64th word occurs given spam times probability that the 65th word occurs given spam, ... plus the probability that we don't have, our email isn't a spam email, so that's 1 minus p, and times the probability that the 23rd word occurs given not spam, times the probability that the 64th word occurs given not spam, and so on, ... Okay, so what do we have here? Well, in the numerator we have p times the probability. We defined this probability of the 23rd word from the list occurring given that our email is spam to be w sub 23. I mean p sub 23, excuse me. So we have p sub 23 times p sub 64 times p sub 65, and then the product of 1 minus pj's, right? Because pj is the probability that the jth word occurs. So 1 minus pj is the probability that the jth word doesn't occur given spam. So we have 1 minus p sub j, and we're taking the product of these, where j doesn't equal 223, 64, and 65, and j is also between 1 and 100. So in other words, this is the probability that the 23rd word occurs given spam times the 64th word occurs given spam times the 65th word occurs given spam, and then the remaining terms in the product are the probabilities that the jth word doesn't occur in the email, given that it is spam. And which words are those? All the words that are not the 23rd, 64th, or the 65th words. And we can write the same thing in the denominator. So P times P sub 23 times P sub 64 times P sub 65 times the product of all the J's from 1 to 100, such that the J doesn't equal 23, 64, and 65, of 1 minus P sub J, plus we have this 1 minus P, and we defined the probabilities, the conditional probabilities of this W events, given that the email is not spam, to be R sub J. So here we defined R sub J to be the conditional probabilities of these words, given that the email is not spam. So again, we're interested in the scenario where the 23rd word occurs, given that the email is not spam, times probability that 64th word occurs given not spam, times probability 65th word occurs given not spam, times the product of the probabilities of the remaining words not being in the email, given that it is not spam. So not being in the email, 1 minus RJ for all the J from 1 to 100, and again, such that J does not equal 23, 64, or 65. And we have our answer now in terms of the desired terms, in terms of P, and in terms of these conditional probabilities, given that the email is spam, and so right here, the conditional probabilities given that the email is spam, and the conditional probabilities given that the email is not spam.